Welcome back to session 16 on combined loadings. This is our fourth portion, our last part that we'll have for the session, and we are going to finally look at the superposition of normal and shear loads to calculate or to look at the state of stress on a given element. And I guess should be careful in saying that superposition of normal and shear loads or normal and shear stress doesn't mean we can't add a normal stress and a shear stress to each other, right? But we can add normal stresses to each other, and we can add normal shear stresses to each other, okay, and then put them on an element, okay. Later we will actually look at how we can do transformations, and there can be equivalent normal stresses due to shear stresses and vice versa. Okay, so in this particular session, what we'll be looking at are types of systems like we have here, where we have maybe a torque being applied and we have some shear stress being induced onto this element, and we may have an axial load, which is causing some normal stress to be induced on this element, or this kind of classic problem where we have a bent beam where you have a px, py, and pz acting on the end, which has the effect of, or the combined effect, the superposed effect of being able to induce shear stresses and normal stresses. Okay. Once again, here's the general procedure. Section the material. We're going to be looking at normal forces, looking at whether or not they are inducing some type of normal stress, looking at shear force components as well, looking at bending, looking at torsion, okay, and then figuring out what the normal and shear stresses associated with these different types of loads would be. And finally, adding the normal stresses to each other and the shear stresses to each other. We've also seen this slide before, which describes the different types of loadings we've covered in the course up to this point. So we've discussed normal forces and normal stresses associated with those normal forces. We've discussed shear forces and the transverse shear stress associated with them in a beam. We've discussed bending moment and the normal stresses, tensile and compressive, that happen, that usually are maximum at the outer surfaces, the top and the bottom of the beam. And we've also discussed torsional moment and how we can think about the torque times the radial distance divided by J. And we've also discussed thin-walled pressure vessels. And actually, I didn't do an example this time where we used thin-walled pressure vessels with their normal stresses to do combined loadings, but there are examples out there. I believe even on one of the exams, the previous exams on the website, you can look and find an example there as well. Okay, so let's do yet another example. Here we have a circular beam or shaft with this configuration, and we have our applied torque here and an axial load P coming out of the end. And this has radius C. What do we expect? Okay, before we do anything else, we expect that this TAP is going to introduce a twisting, okay, on this element, or on the cylindrical shaft, right? And that is going to cause some shear stress, okay? And it's going to be TC over J, right? And C is it's going to be maximum at the outer surface. And what do we expect with the P? Well, we expect that the P is going to be causing a normal load, right, coming kind of out of these sides of this element at A. This one is probably easier to visualize, the P is, but it's not too difficult to visualize what's happening with this TAP. The way I like to do it, okay, is I like to think of what is happening to the structure, what is happening to the beam as it's being twisted, right? And if you can visualize like we've done before when we had all these lines or this grid and how it's deforming, okay, we see that this side is going to go up relative to the side that's farther away. Okay, this side. So this side's going to go up, and this side is going to be going the other direction. And that's how I kind of like to figure out what the arrows for shear stress are going to be doing. So on this side, I'm going to have a shear stress acting upward. On this side, I'm going to have a shear stress acting downward. All right, so that's how I like to visualize what's happening with an applied torque. Let's go ahead and draw an element. Element X, or this element, and then X will say is coming out this direction. All right, so you can kind of see, get your mind wrapped around this. Y is vertical. Okay, so that would be coming up here. So this is the X side, the left side, right over here. This is the right side over here, left side, right side. And we can draw our sigma like we see here. And now let's draw our tau xy. Again, okay, we need to use this a little mental visualization, but like we said, this side's going to be going up, right? So which direction on the left side of this element should it go? Well, it's going to go up, right? Just like that. And in order to keep ourselves in equilibrium, we're going to draw another one, okay, that meets it in this corner. And then I did it correctly this time. We have opposing arrows meeting the bottom right corner. And if we want, we can flip this to see that, yes, if I put X over here on the right side, okay, and I have Y here, then they meet in the upper right-hand corner, and I have tau xy. Remember, right, this is still an X face in the Y direction. It's still positive, just like we have here, okay? But this is a little bit harder to visualize, maybe, okay? Or you can think now, this element, I'm looking through the cylinder. I'm looking through the cylinder to see what I have on the outside. So, you know, I'm going through the cylinder and then I'm seeing my element A. That would be this flip perspective. Calculating the magnitude of sigma and tau xy is pretty straightforward in this example. It's P over A for the sigma, and it's going to be our TC over J. All right, tap times C over J. And J is equal to pi over 2 C to the fourth, and A is pi C squared. So sigma equals P over pi C squared, and tau xy equals 2 times T half over pi C cubed. And that's it, all right? So in this case, right, it was nice. I had a normal stress and I had a shear stress. I just got to put them on the same element. I don't have to worry about adding any normal stresses to each other. I don't have to worry about adding any shear stresses with each other. They just work out. So let's now look at a very much more complicated problem. Okay. In this case, we have the bent shaft. And this is classic. I put something there, the less boring, or is it structure free or less boring lecture? I think, you know, pretty much both of them do it. Jeff Hansen definitely has an example. So if you don't like how I do it, watch those videos. And I've got a couple of them on the website. All right. But I think that more or less, you know, we're doing the same thing. And what we're trying to do is account carefully for the loads and their contributions to normal and shear stresses. And it's not easy to not make a mistake here, okay? What I've seen with the videos online, some people like to do it with the numbers. I like to do it with variables and then plug in the numbers later, okay? And in this case, what I'm going to suggest is that we draw the cross section the number of times that we have an external load applied. Okay, so what I'm talking about, let's go ahead and draw this cross section, 3 times, one for px, one for py, and one for pz. Okay, so we have 3 external loads, and we're going to do 3 drawings of the cross sections, and each one of these cross sections is going to contain the information associated with one of these loads. So let's start with px. All right, so the top one here, contributions from px, and then we'll go to py, and then we'll go to pz. So, okay, px. Well, px, I can kind of transport that force over here, and I know that it's going to be having a force coming out of, like if I transport it, it's going to be coming out, right? And that's going to be a normal stress, straight up normal stress. So one of the contributors is going to be a P over A, or a Px divided by A. Okay, that one is pretty straightforward. The next one, okay, and so what I did is I just kind of said, hey, sigma x coming out, and I said, okay, it's coming out. That's great. The next one's a little harder to see. Okay, the next contribution, Px is causing a bending moment, okay, to be applied in the minus y direction. Okay, can you see that? There's a bending moment in the minus y direction. And what's that going to do to the normal stress at A? If the bending stress, is it going to put in compression or tension? Well, it's going to put it in compression. So I'm going to subtract away the bending stress. Okay, and that's going to be given by this moment being applied to the system, okay, which is Px times B, all right, and it's going to be acting at distance C, okay, so that's where A is distance C, all right, from the neutral axis, and over I. So you see, and you put this over I. So this is the minus my over I. This is where, so this one maybe is a little tougher to visualize, all right? Now, but that's it. Px makes these 2 contributions, and we're done. Okay, it's not causing a shear internal shear force. Okay, here, and so we're going to move to contributions from py. What is happening at py? Okay, so p, or with py. So py is being applied this direction. That's causing this to introduce a torque, all right, in the positive x direction. All right, can you see that? And it has a moment arm of py times b. Okay, so tau t is what I'm going to call, like, this is a twisting or a torque induced shear stress, and we're going to say that it's causing, right, this torque in the positive x. So over here, it's going to be going down, right? That's the positive x, right, direction coming out. So the shear stress that it's inducing is downward, and that can be given by the moment arm PYB, all right, and then so that's the torque PYB, right, and TC over J. Well, C, right, is our quantity again, describing the radius of this shaft, and J is the second, sorry, not the second moment of area, sorry, it's the polar moment of area, okay, which we know is going to be pi over 2 c to the 4th. Okay, so that's one contribution. Now, what else is PY doing? PY is also, if I move it over here, it also is introducing an internal shear force on this surface, okay? And we're going to say it's moving, it's introducing it upward. So the internal shear force introduces an average shear stress, right, on the surface. And you're like, boom, 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 I can see it, I can see it coming up, right? And it's a maximum at the neutral axis for the bending that would be caused okay, about the z direction, okay. And so what are we going to write here? Well, we can first say, okay, there's going to be a shear stress in the positive direction, it's average shear stress, and then we write our 4/3 tau av, okay, and that makes this calculation pretty fast, okay, because it's a max because we're at the neutral axis. Now, I said bending a second ago. Yeah, py is definitely causing a bending, okay, and it's about the z direction, but it's not going to be causing a bending stress at A. It would be causing bending stress at the top or the bottom, but not at A, because A is at the neutral axis. So we could just write, okay, there's no bending stress because A is on the neutral axis. Okay, let's move on to contributions from PZ. All right, so here's PZ, and we can see, oh, it's going to want to, cause some type of normal bending stress, right? And is it going to be putting A into, or is it going to be putting the system into compression or tension at A? Well, it looks like it's going to be causing a bending moment, right, in the minus y direction, okay, similar to what we saw with px. That's in the minus y direction, and that's going to cause there to be a compressive stress here at A. And that can be given by the flexure formula. Okay, what's the bending moment? Well, it's going to be PZA, okay, and then times the y, okay, or I was going to say h over 2, but this is a cylindrical shaft, so it's c divided by I. What about transverse shear stress? Well, it definitely is introducing a internal shear force, right? And that would be in the positive z direction. But A is at the outskirts. It's at the top of that beam. If you think of it being bent that direction, A prime would be equal to 0, and so there's not going to be any transverse shear stress there, okay? Because we're at the top. Okay, so let's just rewrite what we've discovered here. All right, we have contributions from px, contributions from py, contributions from pz. And now, after we write, kind of these basic quantities down, don't get the I and the J confused. All right, I just remember that they're in alphabetical order, and I is less than J. Okay. So now, if we draw our element, okay, A, and this is, it might be good just to go back. Which direction was X? X was coming out this direction, and Y is going up, all right? So here we're saying X is coming this direction, right? So X is coming out of this here, and now we're saying it's going to the right. And we have this direction, Y, positive. And, we want to pick, this is where it's kind of important to pick a plane, okay, or we want it to be 2.5D as much as possible. We don't want to have to be like drawing stresses on other surfaces, on a cube. We want it to be as much as possible to be describing planar stress. And we're gonna have sessions on plane stress in a little bit, but maybe we've jumped things a little bit here. Okay, so what are we talking about here? Well, we have X, we have Y, and we said we had sigma X, okay, this stress coming out like here, and then we had some shear stresses in the Y direction. We have an X, a sigma X in the negative direction. So I've got variables here. I don't have numbers. All right, so I'm just going to draw sigma X like you see here, and I'm going to draw tau xy in a using the positive convention. All right, and to keep things in equilibrium, I had to draw these other shear stresses as well. So this is what the element, kind of a conventional element, would look like, with one axial stress with shear stress acting on it in this plane. So sigma x, we've already written out one expression for sigma x, right? Px over a minus px bc over I. And we also know that we have a contribution, okay, from pz. So we can go ahead and throw that into the mix. And I don't know, unless I plug in values, if it's going to be positive or negative. But if it's negative and I decide I want to draw the element, I could draw the arrows going inward and then use a positive magnitude. For tau xy, all right, we've got to look at the shear stresses, okay, on this element. And we see actually py is the main player here, or is the one we want to keep track of. And we see that we have a contribution, okay, the TV, right, tau v, sorry, that was from the transverse shear stress. That's positive. So why don't we go ahead and we'll put, so tau v, let's put this one down first, okay, which we did. And then the next one is going to be subtracted from it. That's the tau t, right, which is the py bc over j. And that's what you have here, okay? And that's it, all right? Pretty quick, all right? And then you plug in the numbers to get the directions and to get the values that that would be relevant, to that particular configuration. And here's the kind of final question for session 16. All right, this is question number 4, and it's asking, I'm asking, what is the state of stress at location A? And this is at the top of this cylinder, okay? And there's a T-app being applied here. There's an M-app in the positive Z direction, all right? And then there's a PZ as well, and a PX as well. So we're asking, hey, what is the state of stress due to these 4 external loads: M-app, T-app, PX, PZ? And just to kind of conclude this session, we had 4 parts. One was discussing the different types of loadings and, kind of basically what is superposition. The next is, let's look at superposition of normal loads. And we did some examples and there was a problem. And then after that, we said, let's look at the superposition of shear loads and be able to calculate out how these shear stresses add up and get the resulting shear stress at a particular location. And then this last portion that we just covered has to do with coming up with the state of stress at a location, and you're going to be adding normal stresses to each other and adding shear stresses to each other. All right. Thank you for sticking through session 16. And if you have any questions, let me know.